Consider gazing out into the vastness of space, which spans millions of miles. Empty spaces conceal long-forgotten secrets. In July 2025, the James Webb Space Telescope, floating silently in the void, captured something extraordinary: a connection between two cosmic wanderers, Comet SWAN and the visitor from another galaxy, 3I Atlas. These aren't just chunks of ice and dust hurtling through the solar system. Their shared fingerprints, revealed through modern spectroscopy, point to a story that could alter our understanding of the universe. Could these comets be fragments of a shattered world from beyond our stars? Or do they transport clues to something even stranger? Tonight, we're diving deep into the mystery of these interstellar travelers, exploring their paths, their chemistry, and what they might mean for our place in the cosmos. Buckle up, space enthusiasts. This is a journey you won't want to miss. Hit that like button, subscribe, and let's blast off into the unknown together, Comet SWAN. Our first target, SWAN, officially known as SEEN 2020 F8, which lit up the night sky in March 2020. It wasn't discovered by a massive observatory, but by an amateur astronomer, Michael Madiazzo. The comet was spotted in ultraviolet data from the Solar and Heliospheric Observatory's SWAN instrument. Madiazzo noticed a faint glow of hydrogen, a telltale sign of water ice vaporizing as the comet barreled toward the horizon. By May 27, 2020, SWAN reached its closest approach to the Sun, dazzling observers in the southern hemisphere just 64.6 million kilometers away with a glowing tail. But SWAN's brilliance wasn't what grabbed scientists' attention, it was its orbit. With an eccentricity of 1.15, SWAN's path is hyperbolic, meaning it isn't bound to our Sun. It's a one-way slingshot, traveling around the Sun and speeding out of our solar system, never to return. Picture a stone skipped across a cosmic pond, never settling into a predictable orbit. Its steep inclination of 111 further sets it apart, slicing through the solar system's plane like a rogue arrow. SWAN's tale is one of fleeing a brief visitor from far out in space. What forces sent it to us, and what exactly does its journey tell us about the galaxy 3I Atlas? Now, let's move on to 3I Atlas, the third interstellar object confirmed to grace our solar system. On July 1, 2025, the Atlas survey team in Chile spotted a faint line moving at a blistering 58 kilometers per second over 130,000 miles per hour, twice the speed of most comets born in the Oort cloud of our solar system. Unlike SWAN, which barely crossed the threshold of escape velocity, 3I Atlas is a true interstellar bulletin bound by our Sun's gravity from the moment it arrived. Its trajectory, angled at 43 to the ecliptic, cuts through our solar system like a knife, never aligning with the orderly paths of planets or typical comets. Thanks to the team's prompt alert, the James Webb Space Telescope locked onto this fleeting visitor, capturing data that stunned the astronomical community. 3I Atlas passed just 1.8 astronomical units from Earth, close enough to study, but far enough to pose no danger. The chances of catching such a fast-moving object are astronomical. Yet, here it was, a cosmic speedster racing through our neighborhood. So, what makes 3I Atlas so special? And why does its chemistry echo SWAN's in unexpected ways? The real bombshell came when the James Webb turned its spectrograph on 3I Atlas. Expecting the usual water vapor signature, scientists instead discovered a carbon dioxide-rich coma 16 times more than any solar system comet at a similar distance. The CO column density measured 7.6 plus or minus 0.3, a value so high it rewrote the rule book on comet chemistry. Water, usually the star of the show in comets, was barely detectable. This wasn't just an oddity. It contradicted everything we thought we knew about how comets form. Most condense beyond the water ice line, where temperatures allow water to freeze. But Atlas's carbon dioxide dominance suggests it formed much farther out, near the CO ice line at around minus 193 degrees Celsius. This hints at a distant stellar nursery with chemistry unlike our own. Could 3I Atlas have originated in a protostellar disk where carbon dioxide reigned supreme? The James Webb team ran multiple calibration checks, ruling out errors. This wasn't a glitch, it was a cosmic clue, pleading with us to reconsider the origins of interstellar objects. Back to SWAN, Comet SWAN told a different, but equally compelling, story. In April 2020, its hydrogen flare lit up the ultraviolet spectrum. But what stole the show was its dust production, 30,000 kilograms per second, enough to fill an Olympic swimming pool every hour. Unlike most comets, where gas outshines dust, SWAN was a dust factory, scattering sunlight and boosting its brightness. This high dust-to-gas ratio flipped the script on typical comet behavior, making SWAN a gritty, sunlit spectacle. The European Space Agency's analysts tracked this outburst frame by frame, noting how SWAN's coma swelled with fine particles. The connection, compared to 3I Atlas's carbon dioxide-heavy profile, SWAN's dust-dominated signature seemed worlds apart. Yet, when scientists overlaid their spectra, something astonishing happened. A 92% overlap in their chemical fingerprints so statistically strong it ruled out chance. Both comets shared key molecular bands, carbon dioxide, water ice, and faint traces of carbon monoxide. This was not just a coincidence. It was a cosmic connection demanding answers. How could two solaroids, one a system escapee and the other an interstellar intruder, bring along such a precise chemical signature? To understand, let's picture a massive, 5 kilometers wide comet nucleus drifting in the void between stars. Now imagine a catastrophic collision, a supernova, a planetary collision, a shock wave, or the tidal pull of a passing star. Impact models show that such an event could shatter the nucleus, sending fragments flying at different speeds. A few pieces escape entirely, becoming interstellar wanderers like 3I Atlas. Others, like SWAN, might linger in their home system before a gravitational nudge sends them our way. Each section carries the same chemical makeup, a frozen record of its origin. The 92% spectral match between SWAN and 3 Atlas, with a p-value of less than 0.01, suggests they could be shards of the same ancient body scattered across light years and millennia. This isn't science fiction, it's a hypothesis grounded in orbital mechanics and astrochemistry, pointing to a cosmic event that linked these comets long before they reached our sun. The chemical clues don't stop there. The James Webb Space Telescope detected a subtle anomaly in 3I Atlas, a nickel isotope ratio unlike anything seen in solar system comets. The SWAN spectrum revealed faint echoes of an identical isotopic defect. Nickel forged in stars' hearts functions as a cosmic barcode, revealing the type of star system from which these comets emerged. The incongruity with our solar system's chemistry points to a far-off origin, perhaps around a star with a different nuclear background. This isotopic fingerprint strengthens the case that SWAN and 3 Atlas share a common heritage, possibly debris from a cataclysmic event in another star system. Think of it as finding two letters in different mailboxes written in the same raring. The odds of this occurring by chance are vanishingly small, pushing scientists to consider a shared origin, a cosmic family reunion played out across the galaxy. These comets' orbital paths add another layer to the mystery. SWAN's hyperbolic trajectory and 3I Atlas's blistering speed resemble the precise arcs engineers plot for spacecraft like Voyager. The two comets thread through our solar system with a finesse that seems almost intentional, skimming the orbits of planets without colliding. SWAN's outbound climb avoids all planets, while 3I laws past only 0.3 astronomical units from Jupiter, a cosmic bullseye. Such precision is rare for random objects, prompting some to wonder if nature could mimic the efficiency of human-designed flybys. While there's no evidence of artificial direction, and while the resemblance to mission trajectories is striking, these routes point to a more complex order in the chaos of interstellar travel. Or is it just a statistical fluke? The data invite us to keep asking questions even if
Then there's the curious case of 3I Atlas's dust plume. Most comets vent dust in a predictable direction, pushed back by solar radiation. 3I Atlas's plume, however, veers at an odd angle, defying the sun's influence. Polarimetric tests show that this isn't an illusion. The comet looks like it is directing its discharge. Mainstream scientists attribute this to uneven heating or hidden fractures. Only a few, like Harvard's AVI Lobo, raise bolder questions. Is this an indication of physics we do not yet comprehend, or even a hint of something engineered? While the idea of an artificial origin is speculative, the anomaly challenges our models of comet behavior. Every unexpected jet of dust is a puzzle piece, urging us to examine these objects in greater detail. What's next for this cosmic mystery? 3I Atlas's chemistry, particularly its complex organics, has caused a buzz among astrobiologists. These compounds, preserved in ice for billions of years, could contain the elements that make up life. Mission planners are already sketching a 2035 launch to intercept a future interstellar visitor using high-speed dust collectors and flybys inspired by missions like Stardust. Imagine bringing a few grams of material back from another star system, amino acids, sugars, or other prebiotic compounds that could rewrite our understanding of life's beginnings. Meanwhile, NASA's Artemis program is exploring missions that would allow astronauts to closely examine comets and collect samples in real time. The dreaming is brave, human contact with the remnants of a distant world, carrying hints of our cosmic ancestry. As we wrap up, let's reflect on what SWAN 3 and Atlas inform us. Their shared chemistry, a 92% spectral match, and a ratio of carbon dioxide 16 times higher than typical comets, points to a possible common origin. Their hyperbolic orbits, SWAN at 1.15 eccentricity and 3I or Atlas at 58 kilometers per second, mark them as cosmic outsiders. Yet unanswered questions linger. Are they fragments of a shattered world? Could their chemistry hold the seeds of life? The James Webb Space Telescope has given us a glimpse into the universe's deeper story, but it's only the beginning. These comets remind us that our solar system is a crossroads visited by travelers bearing tales of distant stars. So, what do you think? Could SWAN and 3I or Atlas be cosmic siblings? Or is there a stranger explanation waiting? Drop your thoughts in the comments. Hit like and subscribe for more space adventures. The universe is full of mysteries, and we're just getting started.